ponds. As I think all of us tuning in this morning know, stormwater sediment ponds are commonly used as an effective way in accumulating particles and phosphorus from stormwater runoff. But I think we've heard in previous talks, I think I'm remembering one from Mike Trojan and people from the University of Minnesota as well, talk about the downside in that they eventually have the potential to release more phosphorus than they capture during the summer months. Dredging sediment or treating it with alum and iron can control phosphorus release, but these are expensive options. So it's great to have Greg Wilson here this morning from Barr Engineering to tell us about a study evaluating the application of spent lime to stormwater ponds to reduce sediment phosphorus release as an option that has a potential to dramatically reduce the expense of treating phosphorus in these ponds. Greg has more than 32 years of experience in water resources management, including hydrology and hydraulics, water quality modeling, and watershed and lake management planning. He's designed alternative treatment options for internal phosphorus control for more than 25 lakes and ponds. Greg recently completed a project that received Section 319 funding from the MPCA to address carp and sediment phosphorus release that resulted in the delisting of Sweeney Lake on behalf of Bassett Creek Watershed Management Commission. He also assists with NPDES and wetland permitting and SWPPP development and public education and stakeholder outreach. Greg, hey, it is great to have you with us this morning. Why don't you take it away? And the floor is yours.
All right, sounds good. Thank you, Mark. I'm gonna do the full view here on my presentation, and could you let me know if everything is still working properly on your end?
It looks good from my end.
Okay, great. I am imagining that many of you have already seen a version of this talk before. I do have some slightly newer information, but what I really wanted to do realizing that many of you may have seen a version of this talk before is that I'd like to leave some time at the end for more discussion about where do we go next after you've had a chance to kind of see what what our findings are, what we've concluded, and what we're recommending about the use of spent lime to control sediment phosphorus release. I was hoping to have some time towards the end to discuss this in more detail. I do have a hard stop here for another meeting in less than an hour, so I'll have to keep it short as much as I can here to allow enough time at the end. So I'm just going to briefly cover some of the funding that we were able to receive as we worked our way through this subject. Like I said, I'll cover more than just the initial research that was done and was funded through the Minnesota Stormwater Research Council and the Clean Water Fund. And through the Water Resources Center at the University of Minnesota. We had quite a bit of what I would say in-kind contributions from several partners during the course of the research that we've done over the last couple of years. And so I've listed a number of them here in this slide. We've got 3 different cities that have had involvement. And a number of additional cities have expressed interest in addition to those that are listed here. Watersheds as well have expressed quite a bit of interest. And then we did get some assistance through MPCA, both with Mike Trojan as well as with the permitting staff that granted us the permits to do the initial treatments that have been done, and actually a treatment that we are just starting at Oak Knoll Pond for the city of White Bear Lake. So there's some new, there is still some momentum with regard to the original research, and it really does look like this is a promising treatment option for certain water bodies, and and for certain situations in going forward. So like I said, we've got a lot of interest, and part of that is just really a byproduct of what Mark was alluding to. Is there? I mean, there's about 17,000 stormwater ponds throughout the state. Many of these ponds, I mean, I know when I first started working in the water resources field, many of these ponds had been built, were already built 30 years ago. And so, you know, they're maybe reaching the end of what they were designed for. And in large part, it has to do with just the accumulation of phosphorus in the bottom sediments of these systems. And so at some point, they start to release phosphorus when the bottom sediments go anoxic. At the same time that we've got this issue with aging stormwater ponds, we're actively using lime water softening to lime to soften our water. We've got quite a bit of hard water across the state, and so lime is one of the major chemicals that is getting used for water softening. And so spent lime becomes a byproduct of that water softening process. Many of these municipalities that are doing lime softening are having to truck the spent lime product to agricultural fields. And in the case of the St. Paul Regional Water Services, they're doing that at a cost of about $1 million per year, just to truck the spent lime to these agricultural fields. And so, like I mentioned before, phosphorus has been stored up, whether we're talking about lakes or ponds. This is a common problem in the summer where when things go anoxic, phosphorus gets released. There's also decay of organic matter, and any of organic matter that contains phosphorus in these systems will also slowly decay over time. That will release phosphorus. What we have been doing for impaired lakes is it's very common now for us to use alum as a treatment, and basically it gets applied across the surface of these water bodies. It creates a flock layer that settles to the bottom, and it binds up phosphorus. And so the idea that we had for this study initially was, could we use the calcium from spent lime as a substitute for aluminum? And could that be used in the same way that aluminum is getting used to bind up phosphorus? And instead of using the aluminum from alum, we'd use the calcium from the spent lime to do much the same thing. That was the hope. And so that was what led to the original research here, where we're trying to look at, you know, is there another way to reuse spent lime that provides benefit, would hopefully work as well as we know alum works for controlling sediment phosphorus release. And so to get at that question, we proposed a couple different things that we implemented here. It was to do some lab dosing experiments using spent lime from sediment that had been collected from 2 separate ponds. And then ultimately we did do field treatments on a couple different ponds, and then did some post-treatment monitoring to assess whether phosphorus release had been controlled. So we not only did we do field monitoring of these ponds and stormwater going in and out, we were successful at getting one of them pretty well assessed. One of the other ones that was applied, I'll talk less about that just because we did not get a very good data set from that. But then we did come back and along with our post-treatment monitoring in the field, we did do some post-treatment monitoring in the lab to further assess what was happening with the spent lime that was applied there, so that we had some sense for, even in the controlled setting within the lab, whether or not it was working the way we thought it would. And as a byproduct of having done these field applications, we were also able to assess, you know, the methods, the potential approach or methods that we might take for doing these applications in the field. And then we were tracking what it was going to cost, as well as any other permit considerations. throughout the process, because we also wanted to assess how spent lime might compare to other methods for controlling sediment phosphorus release. So like I mentioned before, we're spending a little, just even within the city of St. Paul and its water utility, we're whether you look at it on a per truckload basis, $350. But they are not only are they taking spent lime slurry, similar to what you see in the bottom right hand corner from the city of White Bear Lake, but they are creating filter cake from that, getting rid of the water, and then getting it down to a filter cake, which is what the picture on the left is from the St. Paul Water Utility. That is what is getting trucked out to the agricultural fields at a cost of about $1 million per year right now. And so if we can find another use for spent lime, whether it's in the slurry form or as a filter cake, our thought was that, okay, this could maybe save some of the costs that water utilities are spending right now. And so to give you a sense for how important that might be statewide, here's a list of all the utilities that we were aware of that are currently using spent lime or using lime softening, and so therefore should be generating spent lime. And so it's a pretty long list. It does include White Bear Lake, who was our partner on this project. They like you said are producing the slurry of spent lime. They actually truck the slurry to the St. Paul Regional Water Services, and then it goes through the filter press after that. So they're actually paying, today White Bear Lake is paying St. Paul to handle their spent lime, and then that ultimately goes to ag fields. The reason why we thought this might work well is because we had in the early 90s had previously worked with the St. Paul Regional Water Services to assess the idea of whether or not it might be a method for them to control sediment phosphorus release, which they were dealing with on some of the upper lakes in the regional water services system. As you may already be familiar, St. Paul source water in large part is coming from a chain of lakes, and some of the upper lakes in the system had been having trouble with internal load. So the graph on the bottom left shows what what was our control experiment when we had done some lab testing with spent lime back then, and the release rate without any applied spent lime, was about 6.5 milligrams per square meter per day, which pretty common release rate that we tend to see fairly often for sediment phosphorus release rates for other lakes where there are problems with sediment phosphorus release. So we had tried different dosages back then, and it even just putting 25% of what we had thought we needed to apply was more than enough to control sediment phosphorus release from the lab setting that we had for that. So we kind of knew that this might work just from those early days of having tried it that way. Incidentally, back in the middle 90s, there, even though the St. Paul Water Utility had this information, they did not choose to use it as their approach for controlling internal load in their lakes. They thought it was going to be too expensive to get it applied to each of those lakes, and so they did not go forward with that idea back then. But we knew about this, and so we had thought, well, maybe this would also be an option for controlling phosphorus or treating phosphorus in a filtration setting. And so I had actually experimented with spent lime for stormwater treatment. And then what you see here is a filter system where the flow comes in. It can go through through this filter cake that is shown in the left-hand picture. And then what was coming out was pretty low, and it was able to remove a lot of the dissolved phosphorus from the stormwater flow. So we knew that it had these properties this ability to filter out phosphorus. And it just became a question of, well, would it work in the field at actually controlling sediment phosphorus release and for a longer period of time than and at a field scale that that would compare to what I was just showing for our lab setting. So to begin the lab experiment for this research project, what we did, we were trying to optimize dosages for spent lime and figuring out what we wanted to apply in the field for this more recent study. So we had collected sediment cores, 3 separate ones from each of the 2 ponds that we were evaluating. We looked at the phosphorus fractionations in each one of the cores that we collected. And we were using spent lime. We had collected spent lime from both the St. Paul Water Services and the city of White Bear Lake. The sample is shown in the figure on the left is from the St. Paul water utility, and it actually comes out fairly, it's high amount of water coming out of the clarifier. It's not really looking like the slurry on the right, which came from White Bear Lake. So it actually has much higher water content. And so, in fact, high enough where we just didn't think it was going to work as well. So we really did focus our efforts after this on using the city of White Bear Lake slurry in the rest of the work that we did as a product of both the lab and field testing. But these lab experiments were done to look at after a week of mixing the sediment with the spent lime to see how fractions of phosphorus would change with different dosages of spent lime applied to them. So the next graph shows some of our results with the control in the first section in terms of how much phosphorus was attached to the dry sediment by weight. And then we looked at different dosages, and then we're looking at different fractions of phosphorus and what it was attached to. The top graph shows the core mixture under aerobic conditions, and the bottom graph shows for the same location at Wakefield Pond what the mixture looked like under anaerobic conditions. And what you just see is the more spent lime you add, the more you're forming calcium phosphate in the sediment samples. And sometimes you are doing that at the expense of reducing the organic fractions as well as reducing the aluminum bound fractions of phosphorus. And so we thought, well, okay, this is encouraging. It is forming the calcium phosphate that we hoped it would do in the lab. And it was just a matter of choosing a dose that we would then use in the field setting to apply calcium. So our goal was to kind of be right in the middle of the graph where we could start to see that we'd have higher formation of calcium phosphate. And so that was our intent, was to apply about that amount of calcium try to get that amount of calcium from the amount of spent lime that we'd apply in the field. The one other thing that we were tracking in the lab was how spent lime would change pH. We did know that it's more of a basic chemical coming out of the plant, and that it would probably raise pH. So we were also cognizant of how the different dosages, which these numbers really just correspond to different dose rates that we used for each of the aerobic and anaerobic cores that we had analyzed in the lab. And so you do see that the pH can climb. And so that was another reason why we wanted to try to optimize the dose, wanted to apply enough spent lime so that we would get good calcium phosphate formation, but not so much that it would start to cause pH exceedances above 9.0. And so we had received, as a demonstration of using this in the field, had received permit, had sort of, I'd say, a temporary permitting authority from MPCA to use it both on a stormwater, what technically is a stormwater pond, as well as a public water, which in our case was Oak Knoll Pond. In the end, we ended up needing to choose a smaller pond compared to Oak Knoll Pond for our application. And what I will focus the rest of my talk on about the field application is a pond that is in the Ramsey, Washington Metro Watershed District. It's technically in the it's within their watershed, and it was located in Oakdale. And this is Wakefield Pond. And what we did was we ended up hiring a erosion control contractor who had a an ability to. They had just been they had ordinarily been using their equipment to apply these tackifiers for the use, or their equipment normally is getting used for erosion control. And so they've got the equipment out there to basically go pick up the spent lime from the city of White Bear Lakes facility. And then they had a few hundred feet of hose on the back of their truck. And then what you see is they've got a nozzle at the end of the hose. It is a lot like a fire hose, and they're just spraying that spent lime across the surface of the pond. The photo in the bottom left shows what it looked like just after they had started doing it for maybe 10 or 15 minutes. And then you can kind of see that the spent lime gets applied. They're able to shoot that out maybe 100 to 150 feet. In this case, we had a pretty large elevation drop from where the truck was parked to where the pond is located. And like I said, we must have used about 300 feet of hose to get this down to the pond. And then from there, there's a person holding onto the hose, and they're just spraying it across the surface. It's about 4/10 of an acre of the pond surface area. And then that is basically what the pond, the photo here, the second photo in from the left, shows what the pond looked like immediately after the application. And so it really just kind of creates this milky color to the water. And you can kind of, you start to see what was floating in the water. There's a fair amount of debris and leaf litter and things like that in this pond. It was very high. I mean, it had very low transparency when we started the whole process. And then I'll just click through to a couple more photos that showed what it looked like. I went back out there about 6 hours after the photo to the immediate to the second photo in from the left. And then you could start to see that things were clearing up. Anything that was on the bottom, like this tree limb here and some of the other debris that's on the bottom, became more visible, significantly more visible than it had been immediately after the application. And then I went out another day after this last photo, and then you can really start to see into the pond. In fact, the pond is about 9 feet deep, and you can see to the bottom of it by one day after this application, and where you could never see into the water before this. Now you can see all the way to the bottom. And what's pretty visible to us after having looked at this is that the spent lime is just, it settles to the bottom. It's doing something very similar to what alum does when you do an alum application, except for the material is heavier, and it sticks to whatever it lands on. So it actually, you can see it sticking to the branch, and it's just like whatever it lands on when it comes floating down, it sticks to it. And it really did create a nice blanket over the bottom of the sediment in this case. One thing that we were tracking as a part of this then was the cost of the contractor to do this application. At the time that we did it, it ended up working out. I tried to normalize everything to a per gallon applied basis. It's not to imply that spent lime, that each gallon of spent lime is just as effective as alum. But I do know, that we are generally, especially over the last year, alum treatments have become more expensive. Just for straight alum alone, we're looking at probably anywhere from 6 to 10 times higher cost per gallon applied than what we ended up paying the contractor to do the spent lime, which was 50 cents per gallon. And if we do alum treatments that require, oftentimes when we are working on the alum treatments for smaller lakes, we need a buffered solution. And so a lot of times we're using sodium aluminate for that. And then that brings up the total cost for an alum treatment somewhat higher. So like I indicate here, 5 to 10 times higher cost for doing alum applications. And so oftentimes it just depends on the amount of sodium aluminate that you need to add to it. But over the last year, alum treatments have really, they've gone up 30 to 40% above where they used to be. So I guess the alternative way of looking at this is if spent lime is just even half as effective as alum at controlling sediment phosphorus release, it would still be on a per gallon basis. It still would make a lot more sense to use spent lime instead of alum for a situation like this. And it just becomes a question of, if we increase the scale of doing, if we increase the scale at which we're doing spent lime applications, what will the cost be if we have to do that? Because you can imagine that these erosion control operations, there's a limit to how well this is going to work from shore, at least for larger water bodies, and it may need to be done in a different way at larger scale. So that was another thing that we tried to communicate as a part of this. Then we started doing some post-treatment monitoring to assess at Wakefield Pond anyway, how it was working at controlling phosphorus. So I've got 3 parameters shown on the graph here. This was in pond monitoring. So this would have been, we were taking profile samples in Wakefield Pond, both before and after the treatment. And we did 2 separate applications of spent lime. And so I'll kind of just show you how much we ended up applying here. We did 2,500 gallons in the beginning of June and another 750 gallons in the middle of July. And then you can kind of see that basically in response to both of these, phosphorus would always come down significantly. It came down by half, total phosphorus did. So did the soluble phosphorus after the initial application. There was some algae in the water that dropped down after the initial application. But it didn't totally, this application, it improved the clarity of the water. And so then the algae did grow back after that. And so you can kind of see that. Now the phosphorus came back up. And then this was a pretty dry summer, the summer of 21. But we did have some rainfall runoff events. And so I've got another graph that'll show just how to what degree we thought that was important in terms of how the phosphorus levels changed throughout time. But the algae continued to grow. There was much greater transparency, so there were higher algae levels. But after each one of the spent lime applications, the total phosphorus came down, and then we kind of throughout the rest of the summer with the drought-like conditions, we had very stable, lower phosphorus concentrations. Did not see any real signs of sediment phosphorus release. There was just a couple points, which I'll show in another graph, where we thought there was the potential for some phosphorus release, but it actually appeared as though there was a rainfall event that really impacted the concentration in the pond after that. So I'll move to another graph here to show some of that. This really just shows changes in either phosphorus, total phosphorus, or orthophosphorus incrementally so each sampling event, what was happening during the course of each sampling event, or in the lead up to each sampling event, how much rainfall did we have? And this is kind of where I'm getting to, what I'm getting at here about before, where we had one event. Well, first of all, like I mentioned before, we had significant drops in phosphorus after the spent lime was applied. That's circled here in red, but in blue we had one one time frame where phosphorus increased, but we can see that there was a lot of rainfall, and so we would have had runoff coming into the pond during that event, and that increase. And the only other thing that happened is it appeared as though there was a period where phosphorus stayed low, but the soluble increased in one-time increment, and it appeared as though that corresponded with a significant drop in the algae levels. So that was it looked like an algae die-off event. And then we had one other time frame where it looked like algae was taking off, and so they had consumed quite a bit of the soluble phosphorus, and then we ended up getting some higher one higher total phosphorus concentration, which would have contained algae in it. So that was really just what helped us explain the phosphorus mass balance changes in the pond throughout that first summer of monitoring. Incidentally, I don't have a graph for this, but we have more monitoring data from last year, and these the concentrations from last year actually are actually lower. We've maintained lower concentrations of about 100 or less than 100 parts per billion throughout that last summer, and really no signs of, in fact, really low orthophosphorus, really no signs at all of sediment phosphorus release last summer either. So now we've got about 2 years in a row here at this pond with significant improvements over what you would expect ordinarily, especially considering that our sediment, our dissolved oxygen levels were low enough to where we expected to see sediment phosphorus release, but did not see it. One more follow-up thing that we did do in the lab was we looked at how mobile phosphorus concentrations would have changed, and organic phosphorus concentrations would have changed following the treatment. So we went back out and collected more sediment cores from the same locations that we had analyzed the first time. And the two graphs on the left show mobile phosphorus levels in the sediment cores collected at Wakefield Pond, and the bottom graph is the organic phosphorus fractions that were collected before the treatment. And then we've got graphs on the right-hand side to show how the sediment mobile phosphorus levels changed after the treatment, and including one duplicate sample from the surface of the pond. And really what you see is that the new layer, which is actually lower, it probably had no more than 2 centimeters. It was probably less than 2 centimeters, more like about a centimeter of sediment of the lime slurry would have covered the surface when these samples were collected. And so, but we've got much lower levels of both mobile phosphorus and sediment organic phosphorus in those samples that we collected post-treatment. They no longer have levels that are high enough. This would help explain why we didn't see sediment phosphorus release. And then it also kind of tied up, but I think in the process tied up some of the organic phosphorus that was at the surface of the pond water interface, and so that's reflected in this lower loss on ignition graph in the bottom right. We also noticed too that the dissolved phosphorus levels before the treatment had, were regular. They were at levels less than 1 milligram per liter, levels at which we would expect to see sediment phosphorus release for sure. And we did not actually see dissolved oxygen levels getting to levels that were that low. It actually stayed above 1 to 2 milligrams per liter after the treatment. So in some ways, we believe that the presence of the spent lime actually changes the oxygen demand in the process. And then there were organisms in the sediment cores that we collected, and they were mixing some of the spent lime into the superficial layer of the sediment after we collected these samples. So we thought those were all good signs for how well this was working. And then I come back to the cost comparisons of the proof of concept, both in terms of the cost, its feasibility. We've got the hydroseeder parked here at the top of the hill. Like I said, we've got a couple 100 feet to run the hose down to the pond. You're able to apply all of this from the shoreline. Obviously, this would help make it much cheaper than what we're used to in terms of paying alum application rates. And one of the things that is notable, I think, at both of these ponds that we did do this work at, was that we actually had to stop applying spent lime at Wakefield Pond because the pH did jump up, and we didn't want it to exceed the 9.0 that we had been permitted for. And so we stopped after 3,250 gallons applied there. Our lab dosing rate would have suggested that we'd want to get about 20,000 gallons of the spent lime slurry applied to Wakefield. We couldn't apply all of that because of the pH, the potential for pH exceedances. So we stopped at the 3,200 gallons, but yet, like I indicated in my previous slides, we still saw a significant benefit to just only applying this much spent lime. And so that, on a per gallon basis, like I said, it really seems like it would work well. And then even if you just need to do it more often, but maybe not at the higher volumes to get the desired effect, it would still work out because of the methods that we've come up with to do these applications. The other thing to consider as it relates to permit discussion here is that it does not take very much of the spent lime to get the desired results. We had previously looked at two different ways of considering whether or not spent lime in sediment poses a risk to aquatic life. Like I said, we did see organisms, benthic organisms in our post-treatment core that were definitely alive. We didn't have any issues with that. Didn't see any other adverse impacts. And there were bullheads in the pond. There were tadpoles. Did not see any adverse impacts there. But we have also looked at how our spent lime slurry just all by itself compares to the soil reference values and the soil leaching values. And it really, it does not exceed any of the criteria for that. And back in 2014, when we started using it for stormwater treatment, we had done some testing with the Cereodaphnia zooplankton, and did not see aquatic toxicity from that either, and so it did not result in unwanted toxic conditions from that perspective. And then we're doing continuous pH monitoring when we do these applications to make sure that we don't exceed the pH standard. So these are things that we think, in much the same way that we care about alum treatments and not, having an adverse impact from alum treatments. We've got the same issues with the spent lime, but it's on the other end of the pH spectrum, and so we just feel like we've got a lot of information that would support spent lime as something that we can use without having an adverse impact. So when we start to compare then spent lime to other options for controlling sediment phosphorus release, I've just tried to summarize here our benefits and our drawbacks. Like I said, I think when you compare it to other options, the cost effectiveness is certainly there potentially for spent lime, especially on stormwater ponds. And it just becomes a question of what, if we scale this up to larger water bodies, what would that cost be? We are reusing a material that today is people are looking for ways to dispose of it, or alternative ways to dispose of it that at lower cost. And by the way, the results which we kind of showed in the lab showed that too, that the spent lime was working under anaerobic conditions just as well as it was working under aerobic conditions, which is not always the case with iron filings or other iron additions. Those are redox sensitive and so may not work long term when you have anaerobic conditions. So, but we would like to get longer term monitoring, and so these are some of what we've come out of this with, or some of our conclusions is that we know it's insensitive to redox conditions. That kind of puts it on par with alum treatments. There will be a pH increase, but we know we've got methods for mitigating that. Whether we need to use a buffered solution or not, I'm not convinced that we do. It's probably just a matter of changing the timing with regard to these applications. And so in the field, we've sort of proven that these can work. You get that immediate improvement in transparency and a really good sediment coverage and attachment to the sediment, probably as good or better than alum in how the flock attached to the sediment. So and in the process, it seems like it's actually improving the oxygen demand at the sediment water interface, in addition to the other benefits that we saw in the lab. And so from a cost benefit and permit consideration perspective, really do think this stacks up well, and maybe in many ways is a better approach than anything else that exists for sediment phosphorus release. But what we're lacking is longer term effectiveness monitoring. We'd like to get more of that in the future and continue to monitor things longer term, get more water bodies, try more different dosage rates for this. Think about whether or not we do need to ever buffer it, if, depending on, many of these projects, when they do get done, depending on the funding sources, ideally they may just want to have the full dose applied at once. And so it just, would either require buffering or some other way to mitigate the pH effects. And then, I think there are more things that we could study both in the lab as well as in the field to get better handle on our costs and the cost benefit, and just even the feasibility of doing this in different situations. We don't always have maybe the greatest access and the greatest ability to use the same methods to apply this. And so it just becomes a question of what might that cost at larger scale. So I guess I just want to stop here and allow some time to help talk more specifically about the last couple of questions that I've got on this slide. And I'll open it up at this point because we really do have significant interest from several other cities and watershed organizations that I didn't already mention as partners on the project. So I think with that, I'll turn it back over to you, Mark, or anybody else. Let me know if there are questions at this point. I probably will have to sign off in about 10 minutes for another meeting.
Sounds good. Well, let's get right to these questions in the chat. Well, Brian's got just a comment here that looks like the marl I've seen the bottom of shallow lakes near Lake Michigan, with a link here to that. And then Leah has a question of how often do you have to routinely apply lime to keep the TP low?
Right. So we are actually, so in addition to what I was already talking about and showing here, we are at a larger scale. We're looking at a 4.5 acre pond in White Bear Lake where we are applying this. We have the permit already for that. And I had to do a bunch of calculations there just to even consider just how long might this work. And I guess hopefully this helps answer the question is, I believe that in that setting that it's maybe 5 to 6 years, that we'd have enough stormwater sediment accumulation from the stormwater to that pond in about 5 or 6 years to where it would kind of come back to start having a problem with internal load in this 4.5 acre pond. So I think that if that's at all indicative of many of the other stormwater ponds that where we've got concerns like this, that would be my expectation, is that you might have to plan on reapplying spent lime every few years, 4 to 6 years probably.
Great, thanks. All right, we've got another kind of comment question here from Brian. There are a lot of calcium phosphate compounds. I wonder which ones are forming here. I don't know if that's something you looked into at all, or.
Yeah, I don't think we got that to that level of detail, but that might be another consideration for future study. We were just looking at the typical phosphorus fractionations that we're doing in our lab, and it's not specific to to those individual compounds.
All right, another question here of how big of an effect would vegetation in the pond impact the effectiveness?
Yeah, what I think is happening now, one of the ponds that we did do this on, I didn't have photos of it, but it had duckweed in it when we started. And so, you know what, it was working good, even in that situation. It did have some plants, some submerged plants in that pond. And, you know, the spent lime attaches to the plant. You know, it's whatever it falls on. If it falls on a plant, then, you know, that could maybe limit the, you know, the degree to which you're getting settling on the sediment around the plants. But still, it you know, like one of the other pictures shows is that, you know, like even if you have a tree branch there, I mean, some of that spent lime at first, I mean, it is really a milky substance. I mean, it really, I guess I would say it distributes itself well during the initial application. And like I said, you're using a fire hose, so I mean, you are creating quite a bit. I mean, you really are kind of mixing it into the water when you apply it. So I wouldn't be too concerned about this working in ponds with plants in them.
Great, thank you. We've got another question here. Wastewater facilities using both ponds and mechanical plants most often have an upper pH limitation of 9. However, most use alum for phosphorus removal. Any interest in some pilot studies on, efficiency of comparison of alum versus spent lime?
Yeah, in fact, I think that it's conceivable. Yeah, I am interested in, you know, a range of ideas for a future study, which we did kind of put in one of these slides here that you'll see. But in fact, I think alum could be a buffer to spent lime, or vice versa, depending on how you look at it, because, you know, they're pushing the pH in opposite directions, each chemical respectively. And so, in fact, a lot of times we're using sodium aluminate to buffer alum. Well, in this case, we could have probably used spent lime instead of sodium aluminate and saved quite a bit of cost right there. So no, yeah, but it would be interesting to try all of these ideas in the lab and then just see, you know, if that helps to optimize a future way of doing treatments, especially at a larger scale where, like I said, I think when you start getting to a 4.5 acre pond, we know, okay, we can't just do everything from shore. We got to get out on the water to apply this chemical at least. And so then we're probably looking at equipment that's more like your traditional alum treatment. And so, you know, which is going to change the cost. But then alum costs have gone up. So really do think that spent lime is a potential solution to mitigate that.
And then we've got another kind of follow up on that, that it seems that the lion's share of spent lime is produced in the metro. At what radial distance does trucking costs limit the economic viability of potential use in the outlying areas of Minnesota? Maybe the land application on farm field use scenario has established this already. And I will just add that we are seeing a lot more water treatment facilities move to using lime to remove hardness. And so I would suspect that this is not going to be just a metro kind of produced thing as we move forward with all of these new water treatment facilities now using lime for hardness reduction.
Yeah, I agree with that. And so, yeah, I mean, I do think that that could definitely be part of the cost. Now, the cost that we had for our contractor, they were basically going from they're located in up by Elk River. They're driving down to White Bear Lake water treatment facility, and then they're going to a pond in the same city to apply this, and then, you know, and then going back. So right there, that cost that I had at 50 cents per gallon, you know, included their costs for getting to and from these places that we're talking about. So, I mean, I think to some degree that that, that right there puts this on par with just about anything else that you're already paying to, or for certain, compared to what folks are already paying to drive this to agricultural fields. And even if these cities outside of the metro area are, maybe not having to truck it as far, I guess I come back to these questions at the end is do these fields need the spent lime? I'd hate to take away from something that needs it. But then if it doesn't need it, and do we just not know? Do these ag fields, would it be just as beneficial or more beneficial to actually use it for an alternative disposal option? But these are all things that, when we start to look at the feasibility, it is very interesting because the dynamics are pretty different. I will say that we have had a lot of interest in this technology in the state of Michigan, where they don't maybe have as many options for farm field disposal. And so if there's another way of using spent lime, at least in Michigan, it seemed like that was really going to be important to them. So there's interest in other states too, besides Minnesota. I maybe take one more question, Brooke, before
Sure.
I drop off here.
All right, so we've got a question here of, could you talk a little bit more about the impact of spent lime in aquatic wildlife?
Okay, yeah, and basically I don't really have anything, any downside that I can document. We kind of talked about some of the permit considerations that were brought up before here. There's been testing on it. The filter cake or the slurry itself is all within levels that would support what we want to be at or below for the purposes of looking at sediment tests. There has been the toxicity testing with the spent lime that was used for stormwater treatment and didn't have any unwanted toxic effects from that. As long as we maintain pH at or below 9, we should be in good shape from that perspective. And then just visually, me in the field, like I said, I saw bullheads and tadpoles in the Wakefield pond. They were not adversely impacted. Saw yesterday was at Oak Knoll Pond, saw a turtle there as well. Didn't see adverse impacts from that. And then the ducks and all the other waterfowl, they leave, but you'll go back out the next day and they're back. I mean, it didn't really adversely impact waterfowl either. So that's as much as I can really probably say about that.
Is there any plans to investigate that more, to do some lab analysis on different species to see if there's maybe longer term impacts that we're just not aware of?
Yeah, that probably is worth considering. I don't have anything lined up for that. But I mean, I think that I guess we just don't have any other information. I think that would identify this as a major concern right now. I mean, especially not in comparison to any of the other chemicals that we were talking about. So.
Great. So I know it's
Brooke,
9:57 and you do have to go.
I was
we
going to
just had
suggest.
Yeah, we have 2 more questions left. So could I just put your email address in the chat for these folks to contact you?
Yeah, let me do that. And here's my email address here.
Perfect.
And then, just if you wouldn't mind doing that, and then I'd be more than happy to have another conversation or any other email follow up. I can respond to any other questions or comments or suggestions that anybody has, and at any time here.
Great. Well, we really appreciate you taking time to share this work with us and to have this discussion. We really appreciate it. Thanks, Greg.
Yeah, thank you.
All right. Well, have a good rest of your day, and hopefully we'll see you back sometime soon.
All right. Sounds good. Thank you.